Welcome to this explainer. Today, we are diving straight into the nuts and bolts of setting up a robotics control loop using the Grade 7 Robotics Unit O04 Pacing Guide. If you've ever found yourself wondering how manual control actually works under the hood, well, you are in the exact right place. We're going to look at how humans and machines actually talk to each other to get complex tasks done safely and effectively. Here is our quick roadmap for today. We'll start by busting the remote control myth, then we'll break down how two-way coordination actually works, walk through some worked practice on safe movement, and wrap up with a transfer challenge just for you.
All right, part one, the remote control myth. Let's clear up a massive misconception when it comes to manual control.
So, what is the big essential question guiding this whole unit? It's this: how can humans and robots coordinate through controls? Now hit the brakes for a second and really zero in on that word coordinate. Answering this correctly means we have to completely rethink what remote control actually means. It's not just about bossing a machine around. It's about building a working relationship. Here is the trap a lot of folks fall into: the myth of one-way control. Is this idea that you just mash a button on a joystick or flip a switch and the robot blindly obeys. It's kind of like trying to play a video game with the TV turned off, right? Just a total one-way street. But the reality? The reality is two-way coordination. The human and the robot are actively exchanging data. Think about it. You can't just bark orders without knowing what the robot is actually experiencing out there in its environment. If the robot only listens and never speaks back, you're literally missing half the conversation required to make a reliable system work. Moving on to part two, let's unpack two-way coordination and why feedback is absolutely critical here. Okay, so the secret sauce for a reliable remote control system is what we call feedback data. We're talking about information like sensor readings or the robot's current status that gets sent from the robot straight back to the controller. Why? To inform your next command. It's a continuous flowing loop. You say, hey, drive forward. The robot says, I'm moving, but heads up, I see a wall approaching. And you use that feedback to say, okay, slow down. You coordinate. By looping this feedback data back to the human, we hit a bunch of core focus areas for Unit 04. We're mapping manual controls to behaviors, handling events, and processing user input. But honestly, the biggest takeaway? Through performance testing, we drastically improve the robot's usability and reliability. A robot that talks back and provides feedback is infinitely more reliable than one that just blindly charges forward until it crashes into a table. Which brings us to part three, worked practice. Let's actually build a safe movement sensor feedback loop together. This perfectly illustrates exactly how we program a safe remote control loop, step by step. Let's put you in the driver's seat. Step one, you send a movement command. Say you push the joystick forward. But instead of the robot instantly lunging ahead, we hit step two. The system actually reads back the distance sensor value from the robot. It's actively checking its environment. Step three. The system does a quick sanity check to decide whether it is actually safe to continue based on that sensor data. Like, is there a brick wall 2 inches away? If yes, obviously not safe. And finally, step four, it executes the final action based on that data. If the coast is clear, it moves. If there's an obstacle, it stops or warns you, completely overriding your initial command to prevent a crash. That right there, that is true coordination. Seriously, without that crucial step for reading the distance sensor, your robot is basically driving blindfolded. The second you introduce two-way coordination, you're ripping that blindfold right off. You instantly upgrade the system from a simple, fragile toy into a smart, reliable machine that reacts to the physical world while still being under your manual control.
All right, final stretch. Part four, the transfer challenge. Let's see how you apply these new coordination skills.
So, here is your challenge to wrap things up. Think back to those 4 steps we just used for the distance sensor. Now, how would you weave a completely different piece of feedback, let's say the robot's battery level, into that exact same coordination loop? If the distance sensor logic prevents a physical crash, how would you use that same two-way coordination to ensure your robot never unexpectedly runs out of juice and shuts down mid-task? What exactly would step 2 and step 3 look like for a battery monitor? I will let you chew on that puzzle for a bit. It really makes you see remote control in a whole new light, doesn't it? Thanks for hanging out with me for this explainer, and keep coordinating.